Okay, today we are going to discuss on the postulate 2 of quantum mechanics. Second postulate of quantum mechanics. Postulate 2 of quantum mechanics. Postulate 2 says that to every observable there is a corresponding quantum mechanical operator. Okay, let me write it here. To every observable there is a corresponding quantum mechanical operator. Okay, so what is meant by that? What is meant by observable? Observable means a measurable physical quantity. This means a measurable physical quantity. Physical quantity. Okay. For example, position, or momentum, kinetic energy, okay, or total energy. All these are measurable physical quantities, and such measurable physical quantities are called observables. Okay, so postulate 2 says that to every observable or to every measurable physical quantity there is a corresponding quantum mechanical operator. Okay, and I will explain this one. For example, we have to measure momentum of a microscopic particle. We have to measure the momentum of a microscopic particle. So we set up an equation like px cap psi is equal to px psi. Okay, here px cap, that is an operator. This is an operator, and when we are operating psi function is called a wave function. In the first postulate, you learned that to every microsystem there is a wave. To represent the state of a microsystem, there is a wave function, right? So psi is such a wave function, and when px cap is operating over psi, you get px multiplied by the same psi, and here px is called the eigenvalue. Okay, and this px, or the value what we are getting here at the right hand side, which is multiplied with the psi, and this value will be the momentum. Okay, this value is the momentum. For example, the linear momentum in x direction. So if we get a linear momentum in x depth, how do we get a linear momentum in x direction as the eigenvalue of this equation? Because we got this because we used the particular operator px cap. നമ്മൾ ഈ പി എക്സ് ക്യാപ്പ് എന്ന് പറയുന്ന ഓപ്പറേറ്റർ ഉപയോഗിച്ചത് കൊണ്ടാണ് നമുക്കിവിടെ ലീനിയർ മൊമെന്റം ഓഫ് ദാറ്റ് സിസ്റ്റം ഒരു ഐഗൻ വാല്യൂ ആയിട്ട് കിട്ടിയത്. ഓക്കെ, അതുകൊണ്ട് നമുക്ക് പറയാം പി എക്സ് ക്യാപ്പ് ഈസ് an operator corresponding to the measurable, that is momentum in x direction. അല്ലേ? The measurable or the physical quantity here in discussion is the momentum in the x direction, and corresponding to that momentum we have an operator px cap. Okay, px cap ന് മറ്റൊരു ഡെഫിനിഷൻ ഉണ്ട്, ഒരു എക്സ്പാൻഷൻ ഉണ്ട്. അത് ഞാനിപ്പോൾ ഇവിടെ കൊടുത്തിട്ടില്ല എന്ന് മാത്രമേ ഉള്ളൂ. Okay, so I just wanted to say that corresponding to every measurable quantity of a microsystem, corresponding to every measurable quantity of a system, there exists a quantum mechanical operator. Okay, and if you want to measure the total energy of the system, then we can set up an equation like h cap psi is equal to E psi, where E is the total energy of the system. E is the total energy of the system. And corresponding to this total energy, we have an operator that is h cap. So corresponding to this measurable physical quantity, there is an operator, quantum mechanical operator, that is the total energy operator h cap. Okay, that is the meaning of this postulate. To every observable there is a corresponding quantum mechanical operator. Okay, so let me list some of the quantum mechanical operators corresponding to some physical quantities. Okay, For example, let us write physical quantity here, physical quantity, and I will write the corresponding quantum mechanical operator in the right hand side. Quantum mechanical operator. Okay, the first quantity that we are talking about is position. 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 X. Okay, that is a physical quantity that x denotes the coordinate where we can locate the position where we can locate a microparticle, or for example an electron, or you can consider any particle moving in the x direction at a particular value of x. We can locate that particle at some time. That is the position of that, right? And in order to represent the position, we have a corresponding to this position, we have a quantum mechanical operator. That operator is x cap, okay, x cap, which is equal to x, okay. Here x എന്ന് പറയുന്നത്, that is the position position of the microscopic particle. Actually, that is a multiplication operator. Means whenever you see x associated with some function, you just multiply that function with the x. So x is a multiplier, okay. And if you are taking the x component of the momentum, x component of momentum, x component of momentum, x component of momentum, okay, or px. Px is the x component of linear momentum, and corresponding to this one we have an operator px cap, okay, that is equal to h divided by 2 pi I, h divided by 2 pi I and d by dx. That is the momentum operator, okay, in the x direction. And if we are considering momentum in all three directions, x, y, and z, okay, momentum p, that is equal to p cap is equal to h divided by 2 pi I del, okay. You already know what is del. What is del? Del is equal to I dou by dou x plus j dou by dou y plus k dou by dou z. You already know this del, okay. Del operator. So momentum operator p cap is equal to h by 2 pi I del. And if you are looking at the kinetic energy operator, kinetic energy, let me represent this by T, kinetic energy, and the operator corresponding to kinetic energy, that is T cap, is equal to minus h square divided by 8 pi square m del square, okay, del square. That is a kinetic energy operator, where del square is, what is del square? Del square is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. That is a Laplacian operator. You already know this Laplacian operator, okay. So that is a kinetic energy operator. And if we are considering only the kinetic energy in x direction, okay, so x component of the kinetic energy, x component of kinetic energy, okay, that is tx. That is corresponding to that, there is an operator tx cap is equal to minus h square divided by 8 pi square m and d square by dx square, by dx square. That is the x component of kinetic energy. And if we are looking at the potential energy, and corresponding to potential energy, for example, potential energy we can represent as V, and corresponding to this potential energy we have a potential energy operator V cap, that is equal to V itself, where V is the potential energy of the system. So from this one you can understand that this is a multiplication operator, or it is a multiplier, okay. So momentum operator, that is position operator, is a multiplier, but momentum operator is a differential operator, okay. Kinetic energy operator is also a second order differential operator, but a potential energy operator is a multiplication operator or a multiplier, okay. And if you are looking at the total energy of the system, total energy of the system, for example, we can write it like H, and corresponding to that there is a quantum mechanical operator H cap, and that is equal to, that is the sum of the kinetic energy operator plus potential energy operator, that is total energy operator. That is kinetic energy operator is minus h square divided by 8 pi square m and del square plus potential energy operator is V. Okay, that is a total energy operator. Now we have seen that corresponding to every physical quantity. Okay, these are the physical quantities, or corresponding to corresponding to every observable, there is a quantum mechanical operator. Corresponding to every observable, there is a quantum mechanical operator. Okay. So when this quantum mechanical operator operates over the wave function of the system, we get the value of the physical quantity corresponding to that operator. So നമ്മൾ total energy operator ഉപയോഗിക്കുന്നതെന്നുണ്ടെങ്കിൽ we get the total energy as the eigenvalue. If you are using kinetic energy operator, then we will get kinetic energy as the eigenvalue. So whatever may be the measurable quantity that we are looking into, corresponding to that measurable physical quantity, there is a quantum mechanical operator. That is the second postulate. Okay, I hope you understood the second postulate. Now I am going to talk. Now you may be wondering how I have set up these operators. അല്ലേ, എങ്ങനെയാണ് ഈ ഓപ്പറേറ്റേഴ്സ് ഒക്കെ കിട്ടിയെന്ന് നിങ്ങൾ ഒരു പക്ഷേ ചിന്തിക്കുന്നുണ്ടായിരിക്കാം. So it is easy to get these operators. There are some rules for setting up the quantum mechanical operator. Okay, and before laying that rules out, I will make you familiar with two operators which we will use extensively in deriving all other operators. Okay, so let us talk about first about the position operator. Position operator. Okay, position operator is very simple. Okay, if you are looking into the position of the system moving in the x direction, the x coordinate of that system of x coordinate of that microscopic particle at a particular time will be its position, and that is a position operator. In generally we can talk position you can represent as r, then you can write r as the multiplier, for example, right? So these are the position operator. So we don't need to discuss too much about the position operator. What we are going to discuss too much now or in detail now is the momentum operator. That is very important. Momentum operator. Okay, we are going to set up the momentum operator. Okay, so how to set up the momentum operator? So in order to set up the momentum operator, we are going to take an equation for an electron wave, that is an electron wave can be represented by the wave function corresponding to the electron wave can be represented as psi is equal to a exponential plus or minus 2 pi I x divided by lambda. Okay, where lambda is the wavelength of the electron. Okay, so here we are considering an electron wave in the x direction. Then we can take the psi as a function which represents the electron wave. Okay, when we are giving different values of psi x, then we will get a plot corresponding to the electron wave from this equation. Okay, and from this equation we can get the momentum operator. I will show you how we can get the momentum operator from this one. So we are going to differentiate this equation with respect to x. So differentiate with respect to x. So when we are differentiating with respect to x, we get d psi by dx is equal to a exponential plus or minus 2 pi ix by lambda. Okay, so a is a constant. Let me put that constant here. Now differential of the exponential plus or minus 2 pi ix by lambda. What is that? that is equal to plus or minus 2 pi I divided by lambda exponential plus or minus 2 pi I x divided by lambda. Okay, that is the differential of e raised to ax is a e raised to x. നമ്മൾ അതിന്റെ ഡിഫറൻഷ്യൽ ആണെന്നുണ്ടെങ്കിൽ എന്താണ് എക്സ്പൊണൻഷ്യൽ പ്ലസ് ഓർ മൈനസ് 2 pi ix by lambda multiplied by the coefficient of x. ഇവിടെ coefficient of x എന്താ 2 pi I by lambda ആണ്. അതുകൊണ്ടാണ് ഇങ്ങനെ എഴുതിയിരിക്കുന്നത്. So d psi by dx is equal to this one. Or we can write it like plus or minus 2 pi I by lambda 2 pi I divided by lambda a exponential plus or minus 2 pi I x divided by lambda. Okay, so that is how we can write, and that is equal to plus or minus 2 pi I divided by lambda. What is a exponential plus or minus 2 pi I x by lambda? A exponential plus or minus 2 pi I x by lambda is equal to psi itself. So we can write psi. Okay. So d psi by dx is equal to d psi by dx is equal to plus or minus 2 pi I by lambda into x. Okay. Therefore, we can write like from de Broglie's relation. Okay, from de Broglie's relation, why we are applying the de Broglie relation here? Because electron is a wave, at the same time it can have a particle nature, so it will have the wavelength and also it will have the momentum, because wavelength is a property of the wave nature, property associated with the wave nature, and the momentum is a property associated with the particle nature. And there is a relation between the wave nature and the parameters representing the wave nature and the particle nature. That relation is brought by de Broglie's relation. So from de Broglie's relation, we can write lambda, that is wavelength lambda, is equal to h divided by px, right? Where h is a Planck's constant and px is the momentum in the x direction. Okay, momentum in the x direction. So why we are taking momentum in the x direction? Because we are taking the electron wave in the x direction. So see, we have only one variable x here, not y and z. Okay, so lambda is equal to h divided by px, and therefore we can write like d psi by dx. D psi by dx is equal to, I am going to substitute for lambda here, plus or minus 2 pi I divided by lambda. Then we can write like 2 pi I by h into px, right? We can write like that, 2 pi I by h px. Then what is remaining? Psi. Okay, px into psi. Or if I am rearranging this equation, I can write like h divided by 2 pi I d psi by dx is equal to plus or minus I can write like plus or minus h divided by 2 pi I d psi by dx is equal to px into psi. Now you look at this equation. Plus or minus h by 2 pi I d by dx of psi is equal to px into psi. This is an eigenvalue equation, right? Here the operator is plus or minus h by 2 pi I d by dx, an operator here. Okay, this is operator. Plus or minus h by 2 pi I d by dx, this is operator, and this is a differential operator, and this operator acts on the function psi to give psi multiplied by another value, right? Multiplied by a value, and this value is the eigenvalue. This is the eigenvalue. Okay, and what is this eigenvalue here? That is the linear momentum in the x direction. So this is momentum in x direction, linear momentum in x direction. Okay, so we have obtained the linear momentum in the x direction as the eigenvalue in this equation. What does it mean? And the operator here is corresponding to the linear momentum in x direction. അല്ലേ? px ന് കറസ്പോണ്ടിങ് ആയിട്ടുള്ള ഓപ്പറേറ്റർ ആണ് ഈ കാണുന്നത് എന്നാണ് നമുക്ക് അതിൽ നിന്ന് മനസ്സിലാക്കേണ്ടത്. Therefore, what is the momentum? What is the operator corresponding to the linear momentum in x direction? And that operator, that is the operator corresponding to the linear momentum in x direction. We can write it like a px cap. And that operator is plus or minus h divided by 2 pi I d by dx. This differential operator is the operator corresponding to the momentum in the x direction. Okay. So if we are considering what we want to understand from this one, if the particle is moving in the plus x direction, and then the operator px cap is equal to h divided by 2 pi I d by dx. And if it is moving in the minus x direction, means in the reverse direction, then we can write px cap is equal to minus h by 2 pi I d by dx. Okay, in general, we have to talk only about this one. Particle is moving in the plus x direction. Particle is moving in the x direction means whatever may be the direction of the particle, we can consider that as a positive direction. Okay, so linear momentum operator px cap is equal to h divided by 2 pi I d by dx. ഇത് നമ്മൾ നേരത്തെ എഴുതിയതാണ് നമ്മളുടെ ടേബിളിൽ. linear momentum operator px cap is equal to h by 2 pi I d by dx. അപ്പോൾ നമുക്ക് മനസ്സിലായി എങ്ങനെയാണ് ഈ ഓപ്പറേറ്റർ നമ്മൾ ഡെറൈവ് ചെയ്തതെന്ന്, അല്ലേ? So this operator, linear momentum operator, is very important because from the linear momentum operator and from the position operator, all other operators can be derived. Okay, നമ്മൾ ഇന്ന് തൊട്ട് മുകളിൽ കണ്ട ഓപ്പറേറ്റേഴ്സ് ഒക്കെ ഒന്ന് ഡെറൈവ് ചെയ്ത് നോക്കാം. കൈനറ്റിക് എനർജി ഓപ്പറേറ്ററും ടോട്ടൽ എനർജി ഓപ്പറേറ്ററും ഒക്കെ ഇത് ഉപയോഗിച്ചുകൊണ്ട് നമ്മളൊന്ന് ഡെറൈവ് ചെയ്ത് നോക്കാം. So now we have seen the momentum operator, linear momentum operator. Now, after linear momentum operator, now we are going to derive the kinetic energy operator. Okay, kinetic energy operator. Let us derive kinetic energy operator. So now we can say how to derive a quantum mechanical operator. Before going to the kinetic energy operator, I am going to talk about how to set up a quantum mechanical operator. How to set up a quantum mechanical operator. Okay, I am going to answer this question now. You already know how to set up the linear momentum operator. Now I am going to say generally how to set up a quantum mechanical operator. Okay, first, operator for a coordinate of position is a multiplier. Okay, that we already know. Position operator is a multiplier. Position operator is a multiplier operator. That, for example, x cap is equal to x or r cap is equal to r. It's a moment multiplier operator. Okay, and now we know that the momentum operator. Second thing, we know that the operator for a coordinate of momentum, for example, x coordinate of momentum, px cap is equal to h divided by 2 pi I d by dx. Okay, and what is this I? That is root of minus 1. Okay? I is equal to root of minus 1. So momentum operator, that is equal to h by 2 pi I d by dx. If you are considering the momentum operator, the y component of the momentum operator, we can write it like h by 2 pi I d by dy. Is a component h by 2 pi I d by dz, like that. Okay, so you know the component of the momentum operator in any direction. Okay, and you already know these two things. And for any other physical quantity, we have to write the expression in terms of position and momentum. Okay, every other physical quantity should be represented as a function of momentum and operator. So other physically measurable quantities or observables, all other observables should be written as a function of momentum and position. Okay, and position. For example, Now we can apply this rule. Okay. Then other observables should be written as a function of momentum and position, and then we replace these coordinates by their operates. Okay, and we will see how to set up the kinetic energy operator using these rules. Okay, set up the kinetic energy operator. Let us set up the kinetic energy operator. Then we will understand. You will understand what is actually meant by these rules. Kinetic energy operator. ഒരു kinetic energy operator ഒന്ന് സെറ്റപ്പ് ചെയ്ത് നോക്കാം. Okay, so kinetic energy, for example, kinetic energy in the x direction, that is tx. Sorry, that is tx is equal to half mvx square, where vx is the velocity in the x direction. Or we can write it like m square vx square divided by 2m, right? We can write like that. So what I have done here is I have multiplied the numerator and the denominator by m. That is why I got m square vx square divided by 2m. So there is no change in the value, right? Multiplied by m both in the numerator and in the denominator. And it means that m square v square, what is mv? M into vx is px, because mass into velocity is momentum. So we can write like px square divided by 2m. So kinetic energy is equal to px square divided by 2m. Okay, so we have expressed the kinetic energy as a function of momentum now. That is what we have said here, right? Other observable should be written as a function of momentum and position. Here we can express this as a function of the momentum. Okay, and now we are going to set up the kinetic energy operator. What we have to do is, to set up the kinetic energy operator tx cap, what we have to do here is we have to replace this momentum, okay, with their replace this momentum with the momentum operator. So what I am going to do is 1 divided by 2m. Tx cap is equal to 1 divided by 2m. Okay, now this momentum is replaced by the momentum operator. What is momentum operator? That is h divided by 2 pi I d by dx square, right? So that is equal to 1 divided by 2m, 1 divided by 2m into h square divided by 4 pi square I square, 4 pi square I square d square by dx square. Okay, so that is equal to what is I square? I square is equal to minus 1. Okay, so we can write like minus h square divided by 8 pi square m, minus h square divided by 8 pi square m, and d square divided by dx square. Okay, this is how we are getting the kinetic energy operator. So kinetic energy operator tx cap is equal to minus h square divided by 8 pi square m d square by dx square. So what did we now do? Now we expressed the kinetic energy as a function of the momentum. So kinetic energy is equal to px square divided by 2m. Then in the expression for this kinetic energy, we replaced the px with the px cap in order to get the kinetic energy operator. Okay, so നമ്മൾ മൊമെന്റത്തിന്റെ അടുത്ത് മൊമെന്റത്തിന്റെ ഓപ്പറേറ്റർ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കൊടുത്തു, അത്രേ ചെയ്തുള്ളൂ. അപ്പോൾ നമുക്ക് കൈനറ്റിക് എനർജി ഓപ്പറേറ്റർ കിട്ടും. Okay, so this is how we set up the kinetic energy operator. So dx cap is equal to minus h square divided by 8 pi square m d square by dx square. You can now look at the table that we have already constructed here. Kinetic energy operator tx cap is equal to minus h square divided by 8 pi square m d square by dx square. This is how we got the kinetic energy operator. Okay, and now we can go for the potential. Now we can go for the total energy operator. Potential energy operator you already know, that is a multiplication operator. So we don't need to set up it anymore, right? It's a multiplication operator. Whatever may be the potential energy of the system, the value of that potential energy is the potential energy operator. So that's just a multiplication operator. We don't need to set it up. Now the total energy operator we are going to set up. The total energy operator. Total energy operator. The total energy operator is also called a Hamiltonian operator. Hamiltonian operator. Very important. We are going to hear this term uh, hundreds of times or thousands of times when we are going through the entire portion of quantum mechanics. Hamiltonian operator. We will say this many times. Hamiltonian. So you must know what this is. You should remember always what is meant by Hamiltonian operator. Hamiltonian operator is the total energy operator. Total energy operator. Okay. So this Hamiltonian operator is represented by H cap. H cap. Hamiltonian operator is represented by H cap. So what is the total energy of a system? The total energy of a system H is equal to P square divided by 2m. You already know this. P square divided by 2m. Okay, that is a kinetic energy plus potential energy V x y z. Okay, so P square divided by 2m plus V x y z. What is P here? I have written here P not only as the momentum in the x direction. I have considered all the coordinates x, y, and z. Okay. Now the particle is considered to be moving in a three-dimensional space where x, y, and z coordinates are keeping on changing, and therefore I have not given px here, and instead I give p here. Okay, so we must be very careful about this. Or what we can do here, you may be already knowing how to you already know how to set up the quantum mechanical operator. We have the px cap. Px cap is equal to h square divided by h by 2 pi I, h by 2 pi I d by dx. That is the px cap. Okay, here since we are considering the moment in all directions, okay, we can write it like h by 2 pi I dou by dou x. Okay, h by 2 pi I dou by dou x, and py cap is equal to h by 2 pi I dou by dou y, and pz cap is equal to h by 2 pi I dou by dou z. Okay, so these are the linear momentum operators, x, y, and z components of the linear momentum operator. Okay, so when we are constructing the momentum operator in all directions x, y, and z, okay, then what we have to do, the linear momentum P is equal to Ipx plus Jpy plus Kpz. You can write it like this. Linear momentum P, that is a vector. Okay, the linear momentum P is equal to, that is a vector quantity. So the linear momentum vector is equal to Ipx. Ipx. Here I is not root of -1. This I is unit vector in x direction. So Ipx plus J Py plus K Pz. This is linear momentum. Okay, and so we can write it like momentum P is equal to P is equal to sorry, momentum P, the momentum operator P cap is equal to I Px cap plus J Py cap plus K Pz cap, right? That is what we can do. Now, if we are substituting for Px, Px cap, Py cap, and Pz cap, then we can write it like h by 2 pi I. This is a common factor in all the linear momentum operators, right? Px, Py, and Pz. So h by 2 pi I, and what is remaining? I dou by dou x plus j and dou by dou y plus k dou by dou z, right? So that is equal to h by 2 pi I. What is I dou by dou x plus j dou by dou y plus k dou by dou z? That is the del operator, right? Del operator. You know already this. What is del operator? So that is why I wrote here See, you already know this. We have written here the momentum operator P cap is equal to h by 2 pi I del. Okay, so this is the momentum operator. So I just derived this because we will use this here. So the momentum operator, instead of momentum operator, we will use h by 2 pi I del. That is the momentum operator. Okay. So this is a potential, that is the total energy P square by 2m plus V x y z, and therefore H cap is equal to the Hamiltonian operator. H cap is equal to, now the momentum is replaced by the momentum operator, potential energy is replaced by the potential energy operator, right? So we are going to replace P square by P cap square by 2m plus V cap, okay, in x y z. Okay, I just wrote V cap, it means that V cap x y z. Okay, so that is equal to, sorry, why I wrote cap here, P cap square. Okay, so that is equal to, what is P cap? H by 2 pi I dou by h by 2 pi I del. So we can write it like 1 divided by 2m h by 2 pi I h divided by 2 pi I del square plus V, right? So that is equal to 1 divided by 2m and into h square divided by 4 pi square I square into del square plus V, right? So that is equal to, what is I square? Minus 1. So minus a minus minus h square divided by 8 pi square m del square plus V. That is the Hamiltonian operator. So Hamiltonian operator H cap is equal to minus h square divided by 8 pi square m del square plus V. See, now we can look at our table. We have already written there total energy operator H cap is equal to minus h square divided by 8 pi square m del square plus V. Okay, that is the total energy operator. Okay. So this is how we get the total energy operator. Okay. Yeah, okay. If we are precisely writing it, V is the multiplier operator. We can either write it either like this, or if we want to express it as an operator, multiplier operator, then we can represent V cap itself here. Okay, so that's fine. Okay, so V cap with any function means V multiplied by that function. Okay, so H cap is equal to minus h square divided by 8 pi square and del square plus the potential energy operator. So we have the total energy operator also here now. Total energy operator. Now, in order to wind up our discussion of the quantum mechanical operator, now I am going to show you the last one, that is angular momentum operator. Angular momentum operator. This is very important. This is a very important operator. Angular momentum operator. So, angular momentum operator. Angular momentum operator. Okay. So the angular momentum L. Okay, it's a very important physical quantity of a rotating system that we are going to learn in the next semester, in the second semester. In the second semester, we will learn the particle in a ring, particle in a sphere, and all these things. There we will consider the rotatory motion of the particles, or rotatory motion of the electrons or whatever it is. Okay, microscopic particle. And there it is very important to use this type of operators. So that is why we are learning angular momentum operator now. So angular momentum operator is a very important physical quantity. Okay, especially for that is very important for the rotating systems. Okay, and classically we can get this angular momentum as a vector product of the position and a linear momentum. Okay, so L, that's L, vector L is equal to vector R, that is the position, of cross product by the linear momentum operator p cap. So angular momentum is equal to r into p. Okay, so r cross p, where r and p are the position and momentum vectors. Okay, so angular momentum vector is equal to position momentum vector r cross the momentum vector p. Okay, now if I, j and k are the unit vectors in x, y and z directions respectively, then we can write r, the vector r is equal to I, ix, okay, ix plus j, y plus k z, okay. And we can write the momentum p is as I px ipx plus j py plus k pz. Okay, we can write like this. And therefore, the angular momentum L vector is equal to the position vector, that is I x plus j y plus k z cross, okay, ipx plus j py plus k pz, okay, pz. And this is equal to, you can expand this one and then you will get I ypz minus zpy ypz minus zpy plus j is a vector, unit vector j is a px px minus xpz minus xpz, okay, plus k xpy minus ypx, okay. So you can expand this one, so you have to take the cross multiplication of all the first term with all these three terms, the second term with all these three terms, and the third term with all these three terms, okay. Here you are doing the cross multiplication, that is very important, okay. So at the end you will get I ypz minus zpy j zpx minus xpz plus k xpy minus ypx, okay. And if you want to remember, this is very easy to remember. I, that is a unit vector along the x direction, then within the bracket you are considering the y and z, okay. So if it is I here, within the bracket is ypz minus zpy. What is y? That is a y coordinate, okay, that is a position coordinate. This is the momentum coordinate, the z component of the momentum, okay, ypz minus zpy. When it is j, then you have to consider z and x, not y, okay, zpx minus xpz, and when it is k, then you have to consider x py minus y px. Okay, if you want to remember the order of this one, okay, then you can consider like this: I x y x y z, okay, from here to here, from here to here, from here to here, okay. This is your direction. You can go only in this direction. Now you look at this one, I, that is corresponding to x, right, and then y pz, okay, that is a order. I corresponding to x, then y corresponds to this y, and pz corresponds to this z. That is the order. So this order should be like this. Then then in the next term this should be reverse. If it is y pz, in the next term should be z py. Okay, so that you can remember. When it is j, the direction is j corresponds to y, right? Y ക്ക് corresponding ആണ് j. അപ്പോൾ അടുത്ത ഏതാ വരുന്നത്? z ആണ് വരുന്നത്. അതുകൊണ്ടാണ് ഇവിടെ j കഴിഞ്ഞാൽ പിന്നെ z px, z ഉം x ഉം ആണ് വരുന്നത്. j z px. ഇത് z px ആയി കഴിഞ്ഞാൽ പിന്നെ ഇത് x pz ആണെന്ന് നിങ്ങൾക്ക് അറിയാം. ഓക്കെ, പിന്നെ k ആണ് വരുന്നത്. k വരുമ്പോൾ ഏതാണ്? k എന്ന് പറയുന്നത് z ന് corresponding ആണ് k, അല്ലേ? z ഡയറക്ഷനിലെ യൂണിറ്റ് വെക്ടർ ആണ് k എന്ന് പറയുന്നത്. z വന്നു കഴിഞ്ഞാൽ പിന്നെ ഏതാ വേണ്ടത്? എക്സും വൈയും ആണ് വേണ്ടത്. നോക്കിയോളൂ, അതുകൊണ്ടാണ് ഇവിടെ എക്സ് പി വൈ എന്ന ഓർഡർ വന്നത്. ഓക്കെ, എക്സ് പി വൈ. പിന്നെ വരുന്നത് എന്തായിരിക്കും? വൈ പി എക്സ്. അപ്പോൾ ഇത് ഓർത്തിരിക്കാൻ വളരെ എളുപ്പമാണ്. നിങ്ങൾക്ക് തന്നെ ഇത് എക്സ്പാൻഡ് ചെയ്തിട്ട് ഇതിലേക്ക് എത്തിച്ചേരാവുന്നതേ ഉള്ളൂ. ഓക്കെ, സോ യു ക്യാൻ ട്രൈ ഇറ്റ് യുവർ സെൽഫ്. ഓക്കെ, സോ ദാറ്റ് ഈസ് ആംഗുലാർ മൊമെന്റം. ആൻഡ് നൗ ഇൻ ഓർഡർ ടു ഗെറ്റ് ദ ആംഗുലാർ മൊമെന്റം operator, we can equate this with another equation, that is angular momentum L is equal to I Lx, okay, Lx plus J, okay, J Ly plus K Lz, okay, K Lz എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ, സോ L എന്ന് പറയുന്നത് Lx, Ly, Lz എന്ന് പറയുന്നത് ആംഗുലാർ മൊമെന്റിന്റെ x കമ്പോണന്റ്, y കമ്പോണന്റ്, z കമ്പോണന്റുമാണ്. ഓക്കെ, അത് നമുക്ക് അറിയാവുന്നുണ്ടെങ്കിൽ നമുക്ക് എന്ത് ചെയ്താൽ മതി? ഓരോ ഡയറക്ഷനുള്ള യൂണിറ്റ് വെക്ടേഴ്സ് കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്ത് കഴിഞ്ഞ് കഴിഞ്ഞാൽ നമുക്ക് എന്ത് കിട്ടും? ആംഗുലാർ മൊമെന്റം കിട്ടും. therefore ആംഗുലാർ മൊമെന്റം L is equal to I Lx plus J Ly plus K Lz. അപ്പോൾ ഈ രണ്ട് ഇക്വേഷൻ കൂടെ നോക്കിക്കഴിഞ്ഞാൽ, ഇവിടെ കിട്ടിയ നമ്മുടെ ഈ ഇക്വേഷനും ഈ ഇക്വേഷൻ കൂടെ നോക്കിക്കഴിഞ്ഞാൽ നമുക്ക് എന്ത് മനസ്സിലാവും? Lx is equal to y pz minus z py, അല്ലേ? ഇതിനകത്ത് നിന്ന് Lx is equal to y pz minus z py. You can write like Lx, x component of the angular momentum, Lx is equal to y pz minus z py, and the y component of the angular momentum Ly is equal to zpx minus xpz. Okay, and z component Lz is equal to xpy minus ypx. Okay, so now we know the angular momentum components in the x, y and z directions. The component of angular momentum in the x, y and z directions. And now, corresponding to these different components of angular momentum in x, y and z directions, now we can find out the corresponding quantum mechanical operator. Therefore, what is the quantum mechanical operator corresponding to the x component of the angular momentum? Lx cap is equal to, we just replace the momentum with the momentum operators. That's all, right? Okay, so we get y pz cap minus z py cap. Okay, that is the operator. So we can write it like h by 2 pi I, that is a common factor in both momentum operator. Then what is remaining? Y dou by dou z. Here we have dou by dou z. Y dou by dou z minus z dou by dou y. Okay, so that is the operator corresponding to the x component of the angular momentum. H by 2 pi I, y dou by dou z minus z dou by dou y. Okay, and then what will be the operator corresponding to the y component? Ly cap is equal to z px cap minus x pz cap, right? That is equal to h divided by 2 pi I, then z dou by dou x minus x dou by dou z, right? And similarly, Lz cap is equal to x py cap minus y px cap, that is equal to h divided by 2 pi I, then x dou by dou y minus y dou by dou x. Okay, so now we have got three operators, and these three operators corresponds to the x, y and z components of the angular momentum. Okay, Now I hope you understood what is meant by operator, why it is very important in quantum mechanics, and it is very important because of the second postulate. Because second postulate says that to every observable there is a corresponding quantum mechanical operator, and now you know how to set up a quantum mechanical operator. Okay, so I hope you understood this much, and if you have any doubt, don't hesitate to ask me. And as I always say, please keep on writing when you are watching this lecture. Keep your notebook with you. Okay, whenever I'm writing something here, you also have to take a note of that in your notebook. If you sit back and watch this like a movie or a TV serial, then perhaps you may understand it, that's sure, but you may not be able to write it in the examination because you may not be confident to write it in the examination. You will not feel it as yours. Okay, so you have to write it always whenever I am teaching these things here. So that is the best way to learn the quantum mechanics. I hope you are enjoying this series of lectures in quantum mechanics, and if you have any doubt, please don't hesitate to ask me or leave a comment here in the comment box, and I will try to answer as much as possible. Okay. So thank you for watching and stay tuned.